Okay, I'm back. I'm sharing my screen. I'm trying. There we go. And we're going to talk about chapter 15. Hopefully, audio is going. Let me verify that. Audio is going, yes. Sharing again. Okay, organometallic compounds. We saw them. We saw organometallic compounds earlier. Chapter 7, we took the proton off of acetylene in an acid-base reaction, and we had acetylide as our product. So the organometallic compound there. Here's the organic piece. And the spectator was sodium in this example. And spectators deserve to be crossed off most of the time. Okay, you use that organic anion as a nucleophile in a chapter 9 type SN2 reaction and accomplished a synthesis target. I want to point out, though, these are also strong bases. So if you have protons around, you will destroy this molecule and make it back into acetylene. Any kind of acid with a pKa less than 50. Okay, so this would be a very sad situation if you let that happen. You went to all the trouble to make the anion and you got your acetylene back. In this chapter, we're going to learn how to make organolithiums in a different type of reaction than an acid-base reaction, and Grignard reagents in a different type of reaction. These are, in fact, redox reactions. In this one, we use 2 moles of lithium, and we end up with 2 moles of lithium plus. You're saying, where's the second mole? I see the first one right here. Second one is in lithium bromide. And I can't make a plus sign. There we go. In this one, magnesium goes from zero charge, it's a metal, to +2. It's magnesium 2 plus, Cl minus, carbon minus, and this combination here is magnesium chloride complex ion. Once again, you're making carbon anions, useful for the same things that we use them for up here. Okay, we can do synthesis with them. We can do acid-base chemistry with them. And here's a reminder how you could destroy organolithium compounds and Grignards. If you've mistakenly used a solvent that has some kind of proton, methanol, pKa, it's a low for an alcohol, it's 16, but the fact is it's below 50, and you made your butyllithium into butane, and that is not what you want to do. Similarly, diethylamine with a pKa of 40 would protonate isobutyl magnesium chloride, giving you isobutane, not a happy result. Okay, now solvents are important when making organolithium compounds and Grignard reagents. We need to choose a non-polar aprotic solvent here and a non-polar aprotic solvent here. You can't just choose any ones you want. Alkanes for organolithiums. Ethers are mandatory for a Grignard reagent synthesis because the magnesium is developing a very high charge that needs to be stabilized. The lone pairs on ethers, which are not present in hexane, do you see lone pairs there? I don't either. You need lone pairs in an ether to stabilize this developing positive charge, or else the reaction doesn't happen. So you are getting partial grade for solvents and using the right metal. And that's how we make organolithium compounds and Grignards. I see we're down to 1 person. Did I do something wrong? I don't even know. Rami, did I do something wrong? Yeah. All right, we'll stop the share. Oh, I see everybody now. Sorry putting you on the spot there, Rami. I only saw your name, but I see everybody else is still here. Okay, so next up, we're gonna look more at chapter 15, if I can find it, and I found it. And we're gonna look at section 15.3a, which I'll steal and bring over here, and then I'll share the screen if things go well. Okay. All right, I'm over here and we're zooming and we're sharing the screen. Usually I have this done before you show up, but you know, technical issues take over. There we go. I stole this from section 15.3 of the book. And we have isobutyl lithium. This is a new reaction. We'll do the mechanism underneath. The isobutyl lithium can react with carbonyl compounds. This is new for us. Chapter 16 is about aldehydes and ketones, and we'll review this, what happened in chapter 15 when we get there. And I will send you your chapter 16 today to look at ahead of time before Wednesday. So isobutyl lithium, for some reason, makes a carbon-carbon bond from the anionic carbon here to the carbonyl carbon here. And why would it do such a thing? Well, it's because, as you know, that's a spectator making this an anion with a lone pair, and that's attracted to a carbon that is very positive, being bonded twice to a more electronegative O. So the mechanism we'll do right here. Attack, you get an O minus. That's a terrible arrow. Looks like a hook, doesn't it? Oy. Wow. I'm having a day, aren't I? This guy lost everything. I don't even know what happened there. Okay, you're going to watch me repeat myself all day. It's fine. It slows me down. You like that. We had a lone pair and an anion. We had a lone pair and an anion. We're attacking the carbonyl. Why did we attack the carbonyl? Because the carbon was very positive. Same story here. Better arrow there. Hey, finally an arrow. I'm saving. Okay, and the results we would get, that's why I never answered my question. Why did we attack the carbonyl, although I answered it earlier? We have a very positive carbon when it's double bonded to an oxygen. Positive. And the results that you get, and I'm not going to do the third one, it's the same. This one, and this one. You get an isobutyl group here. You get a propyl group here. You get a new sigma bond, very exciting. New sigma bond to a carbonyl carbon that now is an O minus. And similarly, carbonyl carbon is an O minus and has an isobutyl, a propyl on it. Oh, sorry. There. So that looks similar to this. This looks similar to this. In fact, they're identical. I just crossed off the spectator. And what we get is step 2, HCl. HCl. And we're going to go to isopentanol, and this one, let's use a different color. And this one's going to go to this. Once again, you better do this as a second step. If you had HCl present from the beginning, there would be a disaster in the lab. If you had HCl present with this anion, it would react 1,000,000 times faster than the attack on the carbonyl, and it would generate isobutane and a lot of heat, and isobutane's a fuel. You just did a reaction that created fuel and heat, you would have an explosion. So why is it important to show step 1 is separate than step 2? I know it's a theory course, but we don't like explosions in lab, and we need to know that if you had HCl present from the beginning, you would have an explosion. But we're doing these in separate steps. You make sure step 1 is done, as my lab students did. They even checked the pH if they remember, and then they added HCl after that. And they got their results. The results are very interesting. We have new alcohols, both of them, and we have new carbon-carbon bond here. Well, that looks like a double bond now. Let's not even do that. Let's highlight it. We have a new carbon-carbon bond right there and right there. And synthesis is all about new carbon-carbon bonds. We have a synthesis that makes alcohols, so keep that in your mind when you have alcohols as targets. They can come from organolithiums and Grignard reagents reacting with aldehydes, or as you see down here, a ketone. And the new bond here is right there. And we got an O- in step 1, and O- becomes OH in step 2. So let's put this together and treat this like a baby retrosynthesis before we move on. So say we have a target here. And it looks something like this. And we want to do a synthesis that starts with alcohols of 5 Cs or less. So we got to break that molecule down because clearly it has more than 5 Cs. Now, we got a couple approaches, and one approach, I mean, both approaches will work, but one approach is going to require a lot more work. Oh boy, here we go again. There we go. And the approaches are, I know how to make this bond, or I know how to make this bond. Look at our molecules above. We knew how to make this bond, we knew how to make this bond, and we knew how to make this bond. But if this was my target, I could have made that bond by attacking a C- here on a ketone here. That's 2 approaches. And this has 2 approaches. And the reason I don't like the first approach as much will be clear, I hope. I wanted red. There's our retrosynthesis arrow. And if you remember, that means I know how to make the molecule above the arrow from the one below the arrow. We'll do the same thing down here. The 2 pieces up here would be attack that aldehyde with this organolithium or Grignard, one or the other. They both do the same thing. I don't think I made that clear earlier. Organolithiums and Grignard reagents are interchangeable. You can use either one at any time. And the approach here requires the aldehyde there, and that would be this carbon. Oh, I don't think that works. 1 second. We made that bond, so that was the anion, and the carbonyl was to the right. Where the oxygen is the carbon that got attacked, right? Moving to the top of the screen. The carbon that got attacked was this carbon. So it used to be a carbonyl. There it is. The carbon that got attacked in this approach used to be a carbonyl there. And that's this carbon. And the attacker is everything to the left. The attacker here is everything to the left. Isobutyl and propyl. So we're here. And this thing comes from an alcohol. Don't ever forget, aldehydes and ketones are easily made from alcohols. Sadly, 6 C's. Count them up, 4, 5, 6. So you have work to do if you choose this approach. There's no problem from this here. That came from an alkyl halide. Bromine's popular. And that came from an alcohol. That one, not a problem, 4 carbons. This one here, it's not technically a problem, but it's work. Let's use what we just learned. I know how to make this bond from something with 5 carbons. I can make it from this thing, which I already made earlier, and react it with this thing. Oh, there's an octet violation. That's a 2. All right. So I can make that bond. And these 2 pieces come from this, from an alcohol with 1 carbon, which is fine. It's on my list. And sec-butyl anion comes from sec-butyl bromide. There's a little repetition in this, isn't there? Which comes from, I'll draw it again, this alcohol here, OH. Same as this alcohol up here. The bottom one's more direct, so we'll do our complete answer with the bottom one, and then you could figure out how to do the forward synthesis from the other one. This has 5 carbons, 1, 2, 3, 4, 5. It comes from, okay, my pen's off. Here we go. Well, okay, won't give me that. We're going to do a little oxidation review. That comes from there. This came from an alkyl bromide. Oh, let's not be that messy. With 5 carbons, which comes from an alcohol with 5 carbons. Much more direct approach here. forward synthesis. We got everything we need here. Why don't we just start with the circles on the page? And yes, you're allowed to do this on the tests, not in 241, but 242. We don't need to redraw things. This would be the forward synthesis going this direction. What chemicals do you add? Well, let's see. You're not going to add any chemicals to that to make this because this thing lost a carbon. Ooh, here we go. One of those days, huh? There. 5-carbon aldehyde from a 5-carbon alcohol. That's called oxidation. Do you know how I remember it's called oxidation? We took a carbon that had 2 bonds to H, 1 bond to O, got rid of a bond to a less electronegative H, and replaced it with a bond to a more electronegative O. That's oxidation. The first element that should be in your brain when oxidizing alcohols is always chromium. You have 2 choices of chromium reagents, 2 major choices. Chromic acid, which would be a bad choice here. Please review chapter 10. Primary alcohols with chromic acid create carboxylic acids, not aldehydes. PCC will take a primary alcohol and make an aldehyde. I want to see PCC over that arrow. How do you convert an alcohol to an alkyl bromide and avoid rearrangement? If you used HBr, you're getting 0 points on this one. That thing would rearrange to a tertiary carbocation. PBr3 should be your go-to chemical for converting alcohols to alkyl bromides. Something you'll do on every retrosynthetic analysis in this course and every retrosynthetic analysis in our previous course. How do you convert an alkyl bromide to either an organolithium or a Grignard? You pick one. Tell me you know the chemicals. Lithium and hexane would give you an organolithium. Just hexane. There's hexane. It's not very well drawn, but 6 carbons there. You could have used magnesium and diethyl ether here to make a Grignard. Same deal. Now you have the 2 chemicals required to do the synthesis step here. And let me refresh our memory on the synthesis step. It's a 2-step procedure. You take the organolithium or the Grignard, react it with the aldehyde or ketone in step 1, and in step 2, you add HCl. You need to show me you know it's 2 steps. Remember, we don't want explosions in the lab. So you can indicate that this way. Take these 2 chemicals. Step 1, just tell me you're going to mix them. Step 2, add HCl. And there you have a full credit for I believe it. How many reactions were there? 1, 2, 3, and 4. So it's an 8-point question. We will reconvene and we'll do one that has more points because this is an important retrosynthesis for our test. And I might not even have an alcohol here. It might be an ether, so we can review how to make ethers from alcohols. And I'm going to stop the share. I'm going to hope everything goes well. We will reconvene from this link, so you probably just chill out where you are right now. And I'll never try that shortcut again. And see you in 5.